Hello everyone, this is my third video for the refrigeration engineering. In this video, we are going to discuss about air refrigeration system. What are the advantages and disadvantages of the air refrigeration system and which type of air refrigeration systems are used. So what is air refrigeration systems? In high-speed passenger aircraft, jet aircraft and missile, they require compact and simple refrigeration system with capable of high capacity and minimum power requirement for the requirement of load. When the power requirements needed to transport the additional weight of the refrigerating system are taken into account, the air cycle system usually prove to be the most efficient cycles. The cooling demand per unit for the space are heavy. An ordinary passenger aircraft require a cooling system capable of 8 TR capacity and requires a cooling system of more than 8 TR capacity. So for that, air refrigeration systems are very convenient and economical with less amount of risk. So air refrigeration systems using air as a refrigerant. So there are some merits and demerits of air refrigeration system. So some of the merits are the air is easily available. As we know, air is available in atmosphere and we doesn't require any amount to pay for that. So it is available at no cost. The air is non-toxic and non-flammable. That is the key properties required for refrigerant. Also, the leakage of air in small amount is tolerable. If any other refrigerant leak inside the aircraft, that it is trouble for us. So air is not that much trouble. The main compressor is employed for air compression, so no extra compressor needed. So the design will be compact and it has less capital cost. The air is also light in weight for per ton of refrigeration. So the amount of air required, or we can say weight of the air required for per ton of refrigeration, is less compared to other refrigerant. Also, the chilled air can be directly used for the cooling purpose inside the aircraft or inside the space. The pressure in whole system is low, so piping and duct design are quite simple and easy to maintain. So no high pressurized fluid is flowing through the system. But air refrigeration system has two demerits due to which it is not commercially used, and that is it has low coefficient of performance, low COP, and the rate of air circulation is relatively large. So we have to handle large amount of volume for per ton of refrigeration compared to other refrigerant. So these are the merits and demerits of air refrigeration systems. Now there are different kinds of air refrigeration systems available. From that syllabus point of view, 6 systems are important. The first one is simple air cooling system, second one is simple air evaporating cooling system, third one is bootstrap air cooling system, fourth one is bootstrap air evaporating cooling system, fifth reduced ambient air cooling system, and sixth regenerative air cooling systems. Now we will going to see each and every system in brief. So first one is simple air cooling system. So here is the diagram or line diagram of the simple air cooling system. The main component of the system are the main compression, that is driven by gas turbine. Here the main compression and gas turbine, a heat exchanger, a cooling turbine, and a cooling air fan. The air required for refrigeration system is bled from the main compressor. So first, ambient air is passed inside the system, that is compressed by default in somewhat amount, and that air is known as ram air. So after that air passing from the inlet, that air pass to the main compressor where it get compressed. From that air, some of the air is bled to the combustion chamber and remaining air is passed to the remaining system. So the air which goes into the combustion chamber combusts there and pass to the gas turbine, in which it reduced its pressure, so the work output can be obtained from the gas turbine, and that work is directly utilized for running the main compressor. And the remaining air which is passing from the system is first passed to the heat exchanger, where it gets cooled by the ram air which is bleed from here. So it reject the heats to the ram air and forward to the cooling turbine. In cooling turbine, the air is expanded, so reducing the pressure and temperature, and then it is supplied to the cabin. And the cooling air which is passing from the heat exchanger forwarded to the cooling air fan. So cooling air fan is produce induced draft inside the heat exchanger, so we don't need to put any further equipment for pushing the air, and that air is rejected to the atmosphere, and the air from the cooling turbine is supplied to the cabin at required pressure and temperature. This system is good for ground surface cooling and for low speed flights. So here is the simple air cooling system which is utilized for the low speed flights. So from this line diagram, first we have to understand the TS diagram. In air refrigeration system, TS diagram is important. So here we can see that the TS diagram. So here first 1 to 2 process, that is ramming process, which occurs here, that is 1 to 2. So 1 to 2 is ramming process, but if there is any efficiency then it will be actual. So 1 to 2 dash. From 2 to 3, this is main compression process. So here 2 to 3, that is main compression. So 2 to 3 is isentropic compression, during which there is no heat transfer. And for compression efficiency, there is 2 to 3 days. Then 3 days to 4, that is heat rejection process, that is occurs in heat exchanger. So in heat exchanger 3 days to 4, that is heat rejection. 4 to 5, that is expansion in cooling turbine. So 4 to 5 is isentropic expansion, and if there is isentropic efficiency of cooling turbine, then it is 4 to 5 days. And 5 to 6 or 5 days to 6, that is the 6 point is cabin pressure and temperature. So here we can see that we have full cycle process 1 to 2, 2 to 3, 3 to 4, 4 to 5 and 5 to 6. Okay, now each and every component has its own work. In ramming process, if there is any efficiency, so it is not perfectly isentropic, then what happens? The temperature remains constant, but the pressure will be different. So instead of ideal pressure, there will be some actual pressure which is comparatively low than the ideal pressure. In case of main compressor, if there is any isentropic efficiency or the compression process is not ideally isentropic, then it has same pressure but the temperature will be higher compared to ideal temperature. So it is T3 dash instead of T3. Same as in cooling turbine, if it is not perfectly isentropic, then temperature will be little bit higher compared to ideal temperature. So instead of T5, it is T5 dash. So this is the complete TS diagram for the simple air cooling system. Now what about the COP? So COP will be calculated from these equations. So first, if aircraft is moving with the velocity v, then the kinetic energy will be given by this equation, that is v square by 2000 kilojoule per kg. So what is kinetic energy? It is enthalpy difference actually between second and first point. So H2 minus H1 is equal to v square by 2000, and we know that H is equal to Cp into T. So H2 can be written as Cpt2 and H1 can be written as Cpt1. So instead of H, we are writing Cpt2 and Cpt1. Now taking Cp common and making it transferring it to the right hand side, we are having T2 minus T1 is equal to v square upon 2000 Cp, and then T2 is equal to T1 plus v square upon 2000 Cp, taking T1 to the right hand side. So we are having this equation. Now dividing left hand side and right hand side by T1, we are having T2 by T1 is equal to 1 plus v square by 2000 Cp T1. Now as we have seen on TS diagram that T2 is equal to T2 dash. So if there is ramming efficiency, then temperature remain same, only pressure will going to change. Remember, it is only for ramming process. So T2 can also be written as T2 dash. So T2 by T1 can be replaced by T2 dash by T1 dash. So T2 dash by T1 is equal to 1 plus v square by 2000 Cp T1. Now we know that Cp minus Cv is equal to R. So we can derive equation for Cp as well as Cv. So here we are deriving equation for Cp, that is Cp is equal to gamma R upon gamma minus 1. You can see the process. So putting this value of Cp into the equation, we are having T2 by T1 or T2 dash by T1 is equal to 1 plus v square gamma minus 1 upon 2000 gamma R T1, when R is in kilojoule per kg, when R is in joule per kg Kelvin. Now if we take R in kilojoule per kg Kelvin, then equation becomes 1 plus v square gamma minus 1 upon twice gamma R T1. Okay. Now as we know, velocity of sound, that is A, is equal to gamma R T1. So A is equal to under root gamma R T1. So gamma R T1 can be written as A square. So our equation becomes 1 plus v square gamma minus 1 by twice A square. Also V by A can be written as Mach number. Ratio of velocity to the velocity of sound can be written as Mach number. So v square by a square can be written as m square. So equation becomes 1 plus gamma minus 1 m square by 2. So the efficiency of refrigeration can be written, efficiency of ramming process can be written as P2 dash minus P1 divided by P2 minus P1. Compression work can be written as mCp delta T, that is equal to ma Cp T3 dash minus T2 dash. And turbine work which we are obtaining, Wt is equal to mCp delta T, that is mCp T4 minus T5 dash. Heat rejected during the process 3 to 4, that is mCp delta T, that is T3 dash minus T4. And refrigerating effect produced or heat absorbed, that is mCp delta T, mCp T6 minus T5 dash. So COP can be written as refrigerating effect divided by work supply, that is mCp T6 minus T5 dash divided by mCp T3 dash minus T2 dash. So T6 minus T5 dash divided by T3 dash minus T2 dash. Or COP can also be written in this manner: if capacity is given, then it is written as 210Q divided by MSCP T3 dash minus T2 dash, or MSCP T3 dash minus T2 dash is also power into 60. So power is equal to MACP T3 dash minus T2 dash by 60 kilowatt. MA is the amount of air which is passing from the cabin, or we can say the amount of air required to generate the refrigerating effect, that is Ma is equal to 210Q Cp divided by Cp T6 minus T5 dash kg per minute. Now here if we can see the gas turbine producing power, and this runs the main compressor. Also cooling turbine is producing the power, but this cooling turbine power is utilized to run cooling fan, and the power produced by the gas turbine is used for the running of main compressor. So the power which is utilizing for running the main compressor is the only power that we require to give to the system. The power which is obtaining from the cooling turbine is utilized in running of cooling air fan. So this power is not available for the system for the producing the refrigerating effect. So the power output obtaining from the cooling turbine does not considered for the calculation purpose. So ultimately this is our COP. Now second system is simple air evaporative cooling system. So there are no much difference between simple air and simple air evaporating cooling system. If we can see here, the whole diagram is same. The simple air cooling system as well as the simple air evaporating cooling system both are nearly same. Only the difference is the introduction of evaporator in between the heat exchanger and cooling turbine. So the additional cooling is produced by this evaporator after the heat exchanger before entering to the cooling turbine. So air before entering to the cooling turbine losses it hits in evaporator. In evaporator some different kinds of evaporative medium or material is provided for the additional cooling purpose. So the additional heat is rejected inside the evaporator. So in TS diagram there is also not much difference. As we can see, the TS diagram is nearly same as simple air cooling system. Only the difference is that our 4 point is extended to 4 dash point. Here we can see that 4 to 4 dash. That is the additional cooling or additional temperature lowering, or we can say additional heat loss inside the evaporator. So here this process is denoted by 4 to 4 dash. So earlier in simple air cooling system we are having temperature T4 after the cooling of air inside the heat exchanger, but after introducing evaporator we are having T4 dash. So temperature is reduced T4 to T4 dash. So ultimately we are having less temperature at T5, or we can say T5 dash, compared to simple air simple air cooling system. So in simple air evaporative cooling system the difference is only that the temperature we are obtaining is less at entering to the cooling turbine. So before entering to the cooling turbine, air has less temperature compared to simple air cooling system. So the equations for COP is same as simple air cooling system. Mass of air required is again same as simple air cooling system. Also the power additional, that is mass of evaporant medium, that is required before starting of the aircraft or before starting of the flight, that is mass of evaporative medium is equal to QE into T by HFG, where QE is the heat to be removed in evaporator in kilojoule per minute. T is the flight time in minutes, and HFG, that is latent heat of vaporization of evaporant, that is kilojoule per kg. So only latent heat is rejected. So additional we have to remember the mass of evaporant that is required inside the evaporative system instead of MA. The MA is the mass of air which is required for the cooling inside the cabin. Now next system is bootstrap air cooling system. So here what happens, it is modification of simple air cooling system. In simple air cooling system we are having only single heat exchanger, but in this case we are having two heat exchanger, that is first heat exchanger and second heat exchanger. Both are cooled by only and only ram air. The difference is that here the secondary compressor is introduced in between two heat exchanger. So air passing from the heat exchanger does not go directly to the cooling turbine, but it first pass from the secondary compressor where it get compressed and the pressure rises. Then it again passing from the second heat exchanger where it gets cooled, and then it passing from the cooling turbine. So in case of simple air refrigeration system we have seen that the power produced from the cooling turbine is utilized for the running of cooling air fan. Same as in evaporative system, also the power that is power obtained from the cooling turbine is used for running the cooling air fan. But in this case, in bootstrap air cooling system, the power obtained from the cooling turbine is used to run secondary compressor as well as here at exit jet for the cooling fan, and the gas turbine is for main compressor. Again, only the power required to run the main compressor is counted. This power which is utilizing the running of secondary compressor does not require, as this power is obtaining from the cooling turbine. So this power does not count for the input purpose. So the air passing from two heat exchanger, that is first and second, in between secondary compressor is produced. So the TS diagram has this, that 1 to 2 is ramming process, 2 to 3 is isentropic compressor in first compressor, or we can say in main compressor, and 4 to 5 is the compression process inside the secondary compressor. So what happens in bootstrap? The pressure, or we can say the temperature, final temperature of the air which is rejecting from the compressor, that is T5 dash. So we are having higher temperature, instead of T3 we are having T5. So the cooling of the air is more, so final temperature we are obtaining T7 is less compared to previous system, as the pressure is also higher in secondary compressor compared to simple air cooling system. So the expansion will also occur higher in cooling turbine. So the temperature and pressure both are less compared to simple cooling system. So we are here obtaining T8, that is cabin pressure. So what are the difference in the calculation? So the COP remains same, but the change in mass of air, only change of digit, as the digits are changing here, that is 7 to 8 process is for obtaining the temperature and pressure for the cabin. So here Cp T8 minus T7 dash, and power is same. So basically all equations are nearly same for all the air cooling system. Each and every cooling system having same equations, only the digits are going to be changed as per the TS diagram. So if we can draw TS diagram, then the equation will be easier for you. Now the modification of bootstrap air cooling system is bootstrap air evaporative cooling system. As we have seen the modification of simple air cooling system with simple air evaporative cooling system, same as in bootstrap air evaporative cooling system, evaporator is attached in addition to the two heat exchangers. Same here also, evaporative medium is there and additional cooling is produced by this evaporator. So instead of T5 dash we are having T6. So T5 double dash to T6, this is the additional loss of heat we are obtaining with the help of evaporator, as we have seen in previous system, that is simple air evaporative system. So here also we are having mass of evaporant, that is QE into T by HFG. Again QE is the heat to be removed in evaporator, T is the flight time, and HFG is the latent heat of evaporant. Now next system is reduced ambient air cooling system. So previously whatever the heat exchanger cooling air that is obtaining from the RAM air, or we are bleeding the air from the RAM air for the cooling of main air inside the heat exchanger. But in case of reduced ambient air, now this RAM air is first cooled by the first cooling turbine, and then this air cools the main air which is going to be supplied to cabin. So what happens in this case? The temperature obtaining into the heat exchanger, or the effectiveness of heat exchanger, is going to be higher compared to simple or other system. So comparing to the simple air cooling system, the reduced ambient air cooling system has higher effectiveness of heat exchanger, as we are first cooling the RAM air inside the first cooling turbine. So this air is going to cool the main air which is coming from the main compressor and which is going to be supplied to cabin. So this main air passing through the second cooling turbine, producing cooling effect to the cabin. So air is supplied to the cabin. Now the power obtained from the first cooling turbine and second cooling turbine is utilized to run the cooling fan, as we have seen in case of simple air and simple air evaporative cooling system. So in TS diagram, the diagram is same as simple air cooling system. The difference in the diagram is that the temperature T4. In simple air we are having 4 is nearly about here, T4. So we are obtaining T4 at here right now. So we are having the more lowering temperature when air is exit from the heat exchanger here. And as I have said, the calculating equations are same for the COP, mass of air required, and power. Last but not least, the last system is regenerative air cooling system. So in this case there is a different modification. It is addition. In this, additional cooling is produced by the air which is going to the cabin. So in this case, same as bootstrap air cooling system, we are having two heat exchanger, first one and second one. In first heat exchanger, the air is cooled by RAM air, same as simple air cooling system. But in second heat exchanger, it is also known as regenerative heat exchanger. The air is cooled by the air which is passing to the cabin. This air is bleeded and supplied to the regenerative heat exchanger. Means whatever the air going to the cabin is bleeded for the cooling purpose. So the amount of air which is going to cabin is less compared to other system, but the cooling of this air is more compared to simple air cooling system or bootstrap air cooling system. So what is the difference in TS diagram? So TS diagram is same, but the temperature difference between T7 and T6 is more compared to other system. So it is providing less cooling effect. So the calculating equation for COP is same. Mass of air is same as the other, but M2 is the different. So here M2 is the mass which is passing through the cabin, and Ma is the total air which is passing to the main compressor. Okay. So here are the 6 different air refrigeration systems. Now, which system is utilized for the different aircraft? We can see from this diagram. So here we can see that if the Mach number is in between 0.8 to 1.6, then normally bootstrap and regeneration systems are used in the aircraft. If the flight speed is low compared to jet planes, then the simple air cooling system is utilized. As here we can see that the maximum for the Mach number of 1.4 it is utilized, but the temperature range is quite high. So simple air refrigeration system is normally utilized in the low speed airplanes when there is the temperature requirement is less. One method of overcoming the drawback of bootstrap system is to use part of work derived from turbine to drive a fan which pulls air over the secondary heat exchanger, as we have discussed earlier that the power obtained from the cooling turbine is utilized for running the cooling fan, so which produces the suction effect inside the heat exchanger, so induced draft is produced. So from this diagram we can also select the system. Thank you for the watching.